Hi, this is Calculus 12, Chapter 7.3, Part 1. In Part 1, we're going to be looking volumes as integrals and cross-sections. And this includes disks. Part 2, we'll be looking at the washer method and cylindrical shells. Recall that area is the Riemann sum of the function times the width of the partitions. Similarly, the volume is the Riemann sum of an area function and the thickness of that area. And as we take this limit of delta x going to 0, the volume will be exact. Definition of volume of a solid is the volume of a solid of a known integrable cross-section area A of x from A to B is V of x equals the limit as n goes to infinity, the sum of I equals 1 to n, A of x of I times delta x equals the integral from A to B, A of x dx.
This is important.
That the cross-section area be a consistent shape as x changes. That way x is a single formula, and some setups will be easier solved than other setups. And we can also use symmetry to multiply the integral of part of the object. So let's look at our first object. I'm going to do volume of a sphere. Okay, so we have y going in this direction, x going in this direction. We're going to integrate from negative r to r. And this is our cross-section, and that's a disk. And we have the thickness of the disk, and we calculate x based on r. X squared plus y squared equals r squared. This is a cross-section. As a disk. And we need to determine the limits of integration. And I'm going to do this again. The integral from negative r to r. This is what we think, but we don't write it down. Okay, it's like our substitution. We don't want to mix our u's with our x's, so we don't want to mix our x's with our y's. So don't mix. But we do want to think about what we're doing here. So integral of negative r to r, pi, and x squared can actually be substituted here with some algebra. X squared equals r squared minus y squared. R squared minus y squared dy. Okay, this happens to be fairly straightforward to integrate. Pi, and we have r squared y minus y cubed over 3. And we're integrating from negative r to r. Substituting, we get pi. We're doing the positive r first, so r cubed. And we're substituting r for y minus r cubed over 3 minus, and negative r, so that's negative r cubed. And this becomes positive. There's two negatives. So we have r cubed over 3. And simplifying this, this is 2/3 r cubed. And this is another 2/3 r cubed. So we have 4/3 pi r cubed. And let's look at setting it up a different way. And we could have solved by calculating the volume of a hemisphere and then doubling the answer. So 1/2 v equals the integral from 0 to r. And we have the same function, pi r squared minus y squared dy. So v equals 2 integral 0 to r pi r squared minus y squared dy. And we get 2 pi and r squared y minus y cubed over 3. This is the same. No surprise. And substituting, we get 2 pi r cubed minus r cubed over 3 minus 0. And again, we get 4/3 pi r cubed. Okay, so this is easier to integrate because we have a 0. Here we have a whole bunch of negative signs, maybe not so nice. Okay, so this is more difficult because some of you won't know how to set up your x function. So this is our x, and this is our z going this way, and 0 is down here. So if z equals 0, our width is w. If z equals h, our width is 0. Remember, w is a constant. It doesn't change. X is our variable, so it changes from w and goes all the way down to 0. As z goes from 0 all the way up to h. So our function is w h minus z over h. Okay. And this is our linear interpolation function, as we've done in pre-calc 12. And this is a line. It's linear. And we're interpolating between this value and this value. So let's test this. We plug in 0 for z. So we get h over h, that's 1. And we get 1 times w, that's w. So we'll get this result. Let's plug in h. H minus h is 0 times w is 0. And we get this value. So our linear interpolation function is correct. Our area is x squared. If we want our area in terms of z, then we have this function, w h minus z over h. And this is all squared. Okay, so our volume is 0 to h, and we have a of z dz. And we have 0 to h, w, h minus z over h, and squared dz. We can factor out the w squared because w is a constant, not a variable. And we can simplify this to h over h is 1 and minus z over h and squared dz. And let's expand this binomial because it's easier to integrate term by term for a polynomial. 1 minus 2z over h plus z squared over h squared dz. Now we have integral of 1 is z. Integral of 2z is z squared over h. Integral of z squared is z cubed over 3h squared. And we're going from 0 to h. So we have w squared. And we're substituting h for z, so h minus h squared over h plus h cubed over 3h cubed. We're subtracting 0 because we substitute 0, and here we just get zeros. And then finally we simplify. H squared over h is just h, so these two cancel out, and we get that's a squared. And h squared gets canceled out of here, so we just have h over 3. Okay, and that is the formula for a pyramid. Now, I said the setup can make things easier. And I've labeled this in green. Instead of making our origin here, we could have made z equals 0 here. And then z is equal to h over here, and it's going in this direction instead of this direction. So if z equals 0, x is equal to 0. If z is equal to h, we have x is equal to w. So when z is equal to h, x is equal to w down here. This makes our linear interpolation much easier. X is equal to w times z over h. Okay, so this is directly proportional, where this is inversely proportional because it's got a negative sign. So our volume is still 0 to h, but now we have w z over h squared dz. Again, we can factor out the w squared, 0 to h, z over h dz, and we get w squared, z squared, h squared, so z cubed over h squared, and there's a 3 there, and 0 to h. And we get w squared, h cubed over 3h squared. And we get the same result. H squared cancels out, w squared, h over 3. Okay, a little bit simpler work. We don't have to expand a binomial because of the direct relation between x and z. Okay, now we look at rotation of a function about a line. And it's always good to make a sketch. That way we can determine the correct radius. And by doing a rotation about a line, we get dis. If we're rotating about a line x equals something, then we're integrating with respect to y. If we're rotating about a line y equals something, then we're integrating with respect to x. And usually our axis of rotation is one of the bounds. Okay, here's an example. Find the volume of a solid rotating the region bounded by x equals y squared and x equals 1 about the line x equals 1. So here we have x equals 1. We're rotating in this direction, and we get slices. And when we rotate them, these become discs. We want to note that our slices are perpendicular to the axis of rotation. Okay, if we integrate with the lines running this way, then they're not perpendicular and we don't really have dis. Okay, so we need to solve our limits of integration. So we have x equals y squared and x equals 1, so we have y squared equals 1, so y equals plus or minus 1. And that works out to these limits of integration. So our volume is integrating from -1 to 1, a of y dy, and we have x of y minus x of r. And this is our axis of rotation. Okay, and when we plug this in, we get integral of -1 to 1, and our area is pi r squared, and our r is the function minus our axis of rotation. So we have y squared minus 1 squared dy. And notice that our x of y is smaller than our axis of rotation. So we're going to get a negative value here. Does that matter? It mattered when we were doing area between curves. Here it doesn't matter because we're squaring our result, and that will give us a positive value anyways. So, continuing on, we get integral -1 to 1 pi. We want to expand that binomial, 4 minus 2y squared plus 1 dy, and now it's simple to integrate because it's just a polynomial. We have pi y to the 5th over 5 minus 2y cubed over 3 plus y. And we're integrating from -1 to 1. Now we could have made this simpler by noting the symmetry, and then we can integrate from 0 to 1. But let's continue. So pi, substituting this in, we get 1 over 5 minus 2 over 3 plus 1, subtract -1 over 5, and this is going to be positive 2 over 3, and this is going to be -1. And doing all the adding and subtracting, we get 16 pi over 15. And this is going to be units cubed. Okay, the disk method works when we have a function. The integrating lines are perpendicular to the axis of rotation, or you can think of it as the disks are perpendicular to the axis of rotation. It does not work for a relation. If we have our function and we're rotating about this, we don't have an enclosed area. And if we take this part and rotate it and take this part, we'd have intersecting disks. So it's ambiguous. And we can't solve. No intersection. No limits of integration. You're not likely to get a question like this on the test, but if you get a condition like this on the test, it's probably because you've made an error. So this is a sign that you should check the problem again to make sure that you've set it up correctly. And that completes this lesson.